Purdue University, where he has been there for 20 plus years as a faculty member and is now the director of their University Transportation Center called NextTrans. And true to that acronym, Professor Srinivas Peeta is always looking towards the next generation transportation systems. And his presentation today about vehicle-to-vehicle information flow is in that domain. It's looking at connected vehicle architectures and systems and what that means to our transportation system. Now, Professor Srinivas Peeta and I go back a long ways. I first met Dr. Peeta in the hallowed halls of the Indian Institute of Technology when we were both freshmen in college. So we go back a long way, so it is a personal joy for me to be able to host Dr. Peeta today. After completing his undergraduate at IIT in India, he went on and did a master's in structural engineering. So if there's any structural engineers among you might want to pick his brain as well. So he did his master's in structures at Caltech, and then wisdom dawned upon him, and he said, you know what, I have to be a transportation engineer.
He did.
So then he moved to the University of Texas at Austin, and like many accomplished transportation network modelers, worked with Professor Hani Mamasani at UT Austin, finished his PhD, and then has been a faculty member at Purdue ever since. And of course, Professor Peeta is very well known in the transportation network modeling domain. He has published extensively, made seminal contributions to the field in network modeling. And he served as the chair of the Transportation Research Board Committee on Transportation Network Modeling for 6 years and really elevated kind of the discourse in that field. But beyond that, if you look at his more recent work, he's kind of come a full circle and started seeing the interconnections across infrastructure systems. And so a lot of his work recently has been dealing with looking at the resilience of our infrastructure systems and kind of the interdependencies across infrastructures and how the transportation system functions within an interconnected infrastructure space. So it's a very fascinating work. So with that, I will turn it over to Dr. Peeta, so please join me in welcoming him.
Thanks, Ram, for the very kind words. First time, it's my pleasure to be here, and I would like to thank Georgia Tech, the National Center, and all of you for invitation to make a seminar presentation here. And it's been wonderful so far, the weather-wise as well. It's been really great. So, and I would like to thank Ram for his very kind words, but also for taking the effort to host me here. So, the presentation that I'm going to make today is in the domain of transportation and information systems, in the sense that we are looking at a traffic network and an information flow network, if you want to call it that way, and looking at the interactions between them. So, in the context of information flow, in this study, we are looking at information as flow of raw data. So, raw data means data that's created. It can be information related to the time it took for a vehicle to cross a particular intersection, a particular street, or it can mean information related to some safety alerts. It's just raw data that's out there. So traffic condition information or information such as forward collision warning. And the characteristics of these in the real world are that there are spatial and temporal elements. So there are interactions that show up. And these elements in terms of information can vary because of several factors. Some of them related to the traffic state, because there are dynamics of traffic flow. And then there are other elements that are related to the characteristics of communication networks and constraints that show up from there as well. And as a consequence of that, there are issues such as time delay, so there's decay in terms of information, there's latency, which means when does information reach a certain location, all of that. And so, in one sense, this can be looked upon as an interdependencies among two systems, the traffic system and the information communication system. So, and in the real world, this tends to be a very interesting question, and this is something that has interested me from about 2003 or so. But in 2007 or so, I started finding a student who was really interested in working in it, and from then on, we have moved quite a bit related to this. So, underlying all of it is the notion of what has been done in the literature. And one of the, if you look at the models that are out there are microscopic and macroscopic models. Those that are analytical, even in the traffic flow context, it's very difficult to come up with an analytical model that completely explains the movement of vehicles. So if you bring in the additional element related to an information flow network, where the communication network, it becomes even more difficult. And as a consequence, many of these analytical models are assume what's known as instantaneous information propagation. That is, information propagates at instantaneously or infinite speed, and it covers the whole distance. So if multi-hop simply means that it connects several vehicles simultaneously. And those that are involving simulators, if you look at it that way, so if you look at the network simulator, which is on the communication side, even for a 100-second period, with 1,000 vehicles, it takes 30 minutes. So computational cost is high. And the other thing is using the approach that's been used for microscopic, it's being in this context, it's very contextual, which means it's for a particular market penetration of equipped vehicles, that is vehicles that are equipped to receive such communication, the B2B communication and so on. And it's in the context of specific traffic conditions. And the other type models that people have looked at are macroscopic. And the macroscopic models have primarily looked at the distance that the information travels. And as it states that, because they're macroscopic, they don't look at it at the level of the individual vehicle, they more look at it population-based models. And some of these, of course, are very common in the domain of epidemiology, so where they look at how disease spreads in space. And since they are focused on just the propagation of disease, for them it may make sense. In our context, the macroscopic models that are out there simply do not have any spatial dimension. They just look at population and say whether information will go some distance or not. So in some sense, it does not have the capability to capture the effects of the traffic flow dynamics. For example, you have congestion, queue formation, discharge, you have gaps in terms of where vehicles are, where there is a lot of congestion going on. All of this affects the performance. And then the ability to then have such models described at a network level, because one of the key differences, if you look at the transportation and such models that are out there, is in transportation you have network topologies, and it's the topology that determines how vehicles move, and in that consequence of that is because of that dynamics, how information gets propagated as well. And if you look at the literature, there's an underlying assumption of end-to-end connectivity, and what that simply means is there's the notion that vehicles, the position of every vehicle is known, and then these vehicles can be connected in one shot. And that's known as end-to-end connectivity, so there's this notion of instantaneous propagation of information. And there are several limitations related to that. The first is time delay cannot be captured because the focus is on connectivity rather than in the spatial dimension. So there's no notion of time in that context. So all that is looked at is the distance and whether the connection happens or not. And then it relies on distributions such as Poisson or uniform distribution of equipped vehicles. And as a consequence of that, it's not able to account for the dynamics that I mentioned earlier, congestion formation, discharge, and all of that. And because it's end-to-end, it's known as unicast connectivity, whereas, so what that implies is there is a knowledge of every vehicle, so that there is the connection happening. In the real world, of course, there's mobility of vehicles, so vehicles are moving constantly. And so the notion that we can have that all the time is rather difficult. Under certain contexts it can work out, but if you look at the general case, that becomes rather difficult. So that's the first thing. And the second thing is, it does not account for the fact that when you have high density of vehicles versus lower density of vehicles, or when you have heterogeneity in the characteristics related to that, the actual ability for the vehicles to be successful in the communication also differs. And I'll be talking about that in just a little bit. And then there's no interaction between the dynamic traffic flow and B2B communication. That is, density is not factored, so factors other than distance are ignored in this context. And so there are only certain contexts that they can be applied in. And as I mentioned, the time dimension is not accounted for. So if you look at the store and forward type approaches, so here what you see here is at time t1 you have the instantaneous propagation of vehicles. So you see the vehicles in the red, it means they have received the information. At time t2, then it propagates a little further because there's a catch-up process. So in some sense, we're talking about again instantaneous flow of vehicles, and then it's going further and further. And as I mentioned here, there are certain limitations in terms of how these are used, which I already talked about. So what are the gaps that we need to be looking at? The first one is the ability to describe how the information propagates in both space and time. That becomes important. And there are multiple reasons for that in the real world that I'll be talking about later. But not the least of which is knowing that allows us to address management strategies, not just from the traffic perspective, but also things like safety, things related to whether we can even manage information propagation itself. And that becomes a very interesting problem. And if you try to look at a new generation of strategies, that it can be very interesting. And the ability to look at whether the packet reception is successful. So what that means is whether the information that is being transmitted actually is captured by the other vehicle, the receiver vehicle. And then in the real world, the key challenges are, in addition to distance, there's communication frequency. How often does communication take place? Transmission power. So related to that, there are characteristics that come from the communications domain, which are interference and bandwidth. So there are limitations in terms of capacity. So how information propagates in space and time is a key problem while looking at applications. So that's the underlying motivation for this test. And so there are no existing analytical approach in this context, and the ability to capture these interactions. And as I mentioned earlier, if you're able to understand how these characteristics, the information characteristics are in terms of propagation flow, it can allow us to design strategies in multiple contexts. It can be related to safety, work zone type information, or information on alerts, how they propagate, but also how what can we do to either make them propagate faster or actually slower, both sides. And also designing strategies related to using information to control or manage traffic conditions. Because if one can think about it, a vehicle can also generate raw data on its own experience and pass that information as well. In this study, I'm not focusing on that because all we are looking at is the flow of raw information. All we are looking at is the information propagates, how does the information propagate, at what speed, and so on. In reality, such information has effects, whether they are in relation to the people making decisions based on this information, or in terms of taking actions, for example, related to a safety alert and so on. Vehicles brake, they stop, things like that. So, information flow propagation that we look at, the first thing we are interested in is that wave. And information flow propagation here simply says, differentiates the boundary between the equipped vehicles that are informed and those vehicles that are not. So in some sense we are saying here, there are density of informed vehicles that we say here. And this is the region that's out there. So over time, the informed vehicle zone keeps increasing. So the frontier of that at both ends. So there's a backward wavefront and there's a forward wavefront. So ahead of it, the vehicles are not informed, and so the same thing happens in this direction as well. So the question is, how can we model this? And we seek to obtain capabilities, and I will explain these as we go forward. First, can we come with a closed form solution, and that helps especially on the computational side, and also to get a feel for what happens under certain conditions. And when you have homogeneous traffic conditions, I'll talk about that later on, then we are able to come with a closed form solution here. And also the ability to capture the effects of congestion. So there is the backward propagating traffic wave, there is also the influence of that on the information wave itself. And can we capture that in a realistic manner? And what we are trying to illustrate is that there is this dependency. If you don't capture that, then this notion of instantaneous propagation may be first misleading, and second, may not be sufficient to allow us to address in application context. So what we propose is a macroscopic model on the left side you see the LWR, which is the likelihood richest traffic model that we use. It's the macroscopic one. On the right side, the information flow is represented using a spatial epidemic model. And what we do is we illustrate that there are analogies between them, but we also illustrate that there are differences. So in some sense, the question is how are we leveraging the spatial epidemic model for propagation of information. So, and there are two contexts in which we address. One is homogeneous traffic, which means our traffic density is uniform through the spatial stretch. And then the other one, so in that context, there's a particular conjecture. I'll be talking about what the conjecture is. We're able to count with the linear model, closed form solution, and count with the wave speed. And then under heterogeneous traffic, and heterogeneous traffic, the main characteristic related to that is densities are different in different parts of your traffic facility. That's one. But it can also imply the context where you have information flowing in two directions, maybe, and then that has asymmetries that can lead to interesting outcomes as well. And in that, we have a nonlinear model, and nonlinear model we count as a numerical solution. So this tends to be the more exact solution. This is under a particular conjecture that we are able to count for the solution. And so, as I mentioned earlier, there are two layers. And if you see here, the lower layer is the traffic flow layer, and here S means, I'll talk about that on the next slide. But essentially, what it's doing here on the next couple of slides is it's trying to differentiate between equipped and unequipped vehicles, which means those which are capable of receiving vehicle-to-vehicle communication. The second thing is those equipped vehicles which are already informed about the information that is being spread. So we are talking about a single unit of information that's spreading, and those that are not yet received that information. So there's S and U between informed vehicle and uninformed vehicle. So uninformed vehicle is what we call a susceptible vehicle. So these two belong to the category of vehicles that are equipped to receive information. And when you say unequipped, you don't have the capability to receive information. And based on the dynamics that take place here, we have also the dynamics that take place out there, where this is the upper layer of information propagation. And what we try to do is to characterize these and then the interactions that take place between them. And the lower layer, as I mentioned, is a traffic flow model. We have the LWR model, and it allows us to capture the characteristics such as kinematic waves, fluid formation, discharge, and so on. And the upper level model is, excuse me, it's based on a spatial epidemic model. It's called the SI model. And what it does is, based on the characteristics in the lower layer, it tells which vehicles can potentially communicate and which are successful, or what is the likelihood of the communication between these vehicles. And this leads to the framework that we have here. So from the traffic side, the density of equipped vehicles, so that's where the interaction shows up. Then these are the transmission power and communication frequency relate to the characteristics on the communication side, so the information flow characteristics. And there are environmental factors in the real world, because when you talk about communication that's happening, there are also things like where buildings are located, where are all these other facilities which can in some way bring noise. In our study, we don't include the noise simply because it depends on the particular location or configuration of the streets, the structures that are on them, and so on. But typically the noise is a very small component, even if it's there. So the results that I'll show are actually more optimistic. So when I say more, how to be more careful? They're more conservative, if you want to call it that. So they show speeds which are faster than what they would likely be if noise is brought in as well. And based on that, we count with the characteristics related to communication, so whether they communicate or not, or the likelihood of the communication. And using that, we're able to determine how the wave information spreads. So this is what it is. On the x-axis, you have the distance between the sender vehicle and the receiver vehicle. And on the y-axis, the probability of communication. And I'll talk about how we determine that. And as you can see, the distance, that probability reduces. Then, so that's what is called the communication kernel, this part. And then it flows into the spatial epidemic model, because that's how then we see how the information propagates. Similarly, the density of non-equipped vehicles and the density of equipped vehicles leads to the traffic flow dynamics, because both of those together represent all the vehicles in the network. And these models together allow us to determine the information flow propagation. So that's the underlying process that we have here. So coming to how we use and why we use the spatial epidemic model, the SI. SI is susceptible, infected. So if you look at the second column here, you have epidemiology. The third one is vehicle-to-vehicle communications. So we are trying to illustrate what are the, from an analogy standpoint, what are similarities. So when we say susceptible, in the context of spread of disease, those individuals are susceptible to getting a disease. Similarly, vehicles that have the potential to receive information, which means they're acute. And the other one is informed. So those are infected individuals. So you already have people who are infected. Similarly, we have vehicles that already have information. So this is how we separate those who are likely to receive information or who can be infected versus those who already are infected or already have information. And unacute vehicles are similar to vaccine, people who have vaccine that actually allows them to be resistant to the disease. So you actually start seeing similarities related to that. And there's a rate of infection, just like there is a frequency of communication that allows us to determine how the information propagates. And as I mentioned, I showed in the last slide, we have a kernel function that determines the strength of communication in distance. In a similar way, in epidemiology, they have the strength of infection in distance as well. And as I mentioned earlier, the focus there in epidemiology is the distance. So beyond that, they really don't have the characteristics associated with traffic, which has traffic density variation, the dynamics associated with that, and so on. And so we have a single unit of information that propagates, and we assume that information is stored and broadcast throughout this horizon of interest. So if you look at it with this context, we can see what are the similarities and differences. From a modeling standpoint, now you look at the network. In epidemiology, the disease can spread in all directions. Like we say in a plane, just because they can go in all directions. And in our context, the topology of network restricts how the vehicles move, but in terms of information, there is that correlation there that shows up. Population movement, disease can spread with or without movement of population, because you can have diseases that spread to air and other mechanisms, waterborne and so on. Whereas in our